Alright, so I'll talk about quantum simulation. Digital mostly, with some relative time at the end. And the theme will be adaptive algorithms. You heard a little bit about that. But because the audience is quite diverse within quantum simulation, I will give a little bit of an introduction, maybe a little bit more than private talks. So the goal here is to simulate fermionic systems. And the Hamiltonian you see here in the top is inverse quantization. So you have the kinetic terms and you have the Coulomb terms between electrons and ions. And then the standard classical preprocessing step is that we choose a basis and we write down the Hamiltonian cycle quantization. It's not necessary to do this, you can have quantum simulation without this step, but it's a very common first step. So I'll stick with that. And of course, fermions obey these computation relations. And we'll see how to build these in the qubits. So toward that, let's look how we go from first quantization to second. Still in a classical sort of way. All this is being done, of course, in classical simulation as well. So you start, you have some state, in this case the electrons, and instead of writing down the spatial orbital wave functions that are explicitly antisymmetrized, you can express the very same thing in a binary notation, where you have zeros and ones denoting the perturbation number of the particular orbital. So in this case, orbitals 2 and 4, and when I say orbitals, I mean spin orbitals. For gravity, I'm just going to say orbitals. So here, 2 and 4 are occupied, and we use the shortcut of zeros and ones to identify which orbitals are occupied. So this is kind of a nice first step going towards the quantum processor, because then we have qubits, so we have naturally binary sense to our encodings. And we'll use this, the most kind of maybe obvious way of mapping, which will be exactly what I showed you in this previous slide. So each qubit represents an orbital, and the zero state of the qubit will be the unoccupied version of the orbital, and the one state will correspond to the occupied. So here you have as many qubits as orbitals you're keeping for your problem, right? And you can keep more and more orbitals, you don't have more exact simulation. So the next step to worry about is how do we represent operators from the fermionic side to the qubit side. And the way to do this, or at least under this sort of Wigner approach, is to look at the raising and lowering operators and represent them not only by raising and lowering the state of the qubit, but also building in the fermionic relationships. And we'll do that by having these Z strings, these operators over here, which act on all the qubits that are numbered below the one you're looking at. Right? So this allows you to respect fermionic focus. So this is a kind of a very quick overview of how we map fermionic qubits. There's other ways. I'm just going to stick to this for this talk. And this stuff we do no matter what kind of algorithm we do. If we do phase estimation or other similar approaches or variational approaches, I'll mostly focus on variational approaches today. So big dreams are just the same thing as we learned in undergraduate quantum, the variational approach. The only difference is that now we do it jointly between the classical computer and the quantum computer. So we start with representing some trial state on our quantum computer. And this is the difficult part for classical computers, storing a large state. So we prepare some state. Ideally, this state, for some value of the parameters, the parameterized state, contains the exact solution. We'll get back to that. And then we make measurements, still on the quantum computer. And then we feed the outcome of these measurements on a classical computer, which helps us do the optimization. So on the classical computer, we vary the parameters and we feed back in updated values for these parameters. And that way, ideally, we converge to the state we're looking for. Let's see the ground state here by varying these parameters. So here you see a parameterized circuit like that. I have some yield theta, which is a large unitary acting on all the qubits, and we break that up into different unitaries, each carrying 1 parameter. So here's my outline. I'll tell you a little bit about ansatz that have been used. So how do we choose this yield theta? Then I'll talk about our approach, which is adaptive approaches. And if I have time, I might need to skip this last part, but I can talk about it offline. I'll talk about pulse level EQ. All right, so one ansatz that's pretty well known and was used in this early work by IBM is a hardware efficient ansatz. And with this ansatz, kind of takes the position that let's just take gates that are easy to do on a particular platform, ideally native gates. And parameterize them, or some of them. In this example, we parameterize single qubit gates, and the backward gates are not parameterized. And then just layer them, and just have some depth. This part, how much depth should be is not what we find. So enough depth to hopefully find, parameterize the parameterized state to contain the exact state. But there's there's an appeal to this, of course, that you are using native gates, but also you are possibly sampling too much of the Hilbert space. And that can lead to this issue of part plateaus that was mentioned before. Another common ansatz is UCC or UCC-Z, which takes terms, fermionic terms from Hamiltonian and higher order fermionic terms. You can hopefully see them over here. And you exponentiate these terms. It's A dagger A, dagger AA, different indices. And then you create the unitary version by exponentiating these, and you give a parameter to each of these. So in the unpolarized version, you have a sum of these terms with the exponent. In the telluride, you break it up, and you do these gates also in some fashion where you alternate. Note that if your tellurarization is finite order, there's no well-defined way to tell you what order I should put these gates. There's a hope that you could absorb any differences into the optimization. We have shown that that's not the case. So for low order tellurarization, you don't get unique things depending on how you order. And there's been, in both cases, there's been experiments that have used these ansatz. So going back to our work from 2019, we looked at the literature, we looked at these different ansatz, and what we realized is that they can lead to very long circuits. They're not problem tailored for the most part. So you don't, especially the hardware efficient ansatz, knows nothing about the problem you're solving. It has the same gates, and then you're trying to minimize the objective function, no matter what the Hamiltonian is. And of course, as I mentioned, you have possible trainability issues. So our main contribution in this early work was to put forward the idea that you can make your ansatz adaptive. In other words, you can create it dynamically as you're running the algorithm. So this is the main idea. I start from a simple reference state. It could be, in general, some product state. It doesn't have to be, but it makes our lives easier if it is. And then we're only adding a small number of operators, and we're adding them in an iterative way. So at every step of the algorithm, we're adding an operator. That operator carries a variational parameter along with it. And we determine what operator to add next based on measurements of the objective function or some function of the objective function on the quantum computer. So schematically, you can think of running the algorithm and then repeating this and adding operators as you go along. So hopefully, as you add these operators, you should converge to the solution you're looking for better and better. So this is a very general idea, and it doesn't have to be tied to variational approaches. It's quite general. But let me go into a little bit more details about what enters here and what decisions you have to make. So one thing is, what are these views of J's, right? How do I decide in the beginning what are my options for the operation I'm going to have? We call this an operator pool. You already heard this term. So this is a very critical part of adaptive B3. And if you choose a bad operator pool, like we heard before, you can fail, and that's very natural. So once you choose your operator pool, and you can choose it according to your hardware connectivity, you can choose it many different ways. You have to make the decision of which of these operators you add first, exponentiated version of these operators. And the criterion we use for that, at least in the early work, people have done follow-up work looking at other criterion, is a gradient criterion. So you look at the gradient of the objective function at the step you are at in the algorithm with a different option. So this A, imagine it's A sub j. So you have these different A's consisting of which your operator pool consists. And you're essentially looking at which one will have the most effect on the energy by looking at the gradient. And what's nice if you do that is that you can show quite simply that this is the same as the mean value of the commutator of the Hamiltonian of that particular candidate operator, which in turn is something you can measure on the hardware. So you're making measurements on the hardware that are telling you how do you grow your ansatz next. All right. So this is I stole this from a postdoc. All right. So let me show you just what I already said in a schematic way. So we start from some initial state, or you can think of this as the state at the iteration k. This is the you have created at that point. You take each of the operators in your pool, and you test this gradient, the derivative of the objective function for each of them. And then you select them which has the largest gradient or derivative. You add that onto your ansatz. So now you have a new ansatz at the step, at the kth iteration, and you re-optimize all the parameters. Okay. And then you keep going. Okay, so if you're not happy with what you have up to a point, you can keep iterating. And you stop when these derivatives are small, right? In the perfect world, they'd be zero. In practice, they're just small, and you stop. All right, so let me show you some simulations based on this. This is early work. I'll show you some more recent work from the last year in a moment. So these are the first things we did. We started with the fermionic pool, which is the same operators that UCC is uses. So these A dagger A's and A dagger A dagger A. Especially because we're interested in comparing to UCC's data time. And we simulated 3 different molecules here: lithium hydride, beryllium hydride, and hydrogen 6. Hydrogen 6 is a system that chemists like to use to benchmark their class algorithms as well, because it has strong correlations. So let me guide you through these plots. So in the top plot, we're plotting the error from the exact solution. All these are small enough systems, so you can solve them classically. And you can compare, if you run this algorithm, how well does it do compared to the exact solution. The y-axis is the logarithmic scale. And the x-axis, we have the interatomic distance. All right, so here we have a few different versions of adapt, depending on how much we tighten it. So epsilon 3, showing over here, the red one performs, the brown one performs better because it's a tighter threshold, which means we're adding more operators, right? Not surprisingly, it works better than the rest. And you see that we quite easily beat UCC's D, which is a fixed ansatz. And then you can compare how many operators, or how many variational parameters rather, this adapt technique has versus the UCC's D fixed ansatz. And you see that while you are getting a better result, you're learning the energy more, you have fewer variational parameters. So you can actually win on 2 fronts with this, which tells you that UCC's D is not as economical as it can be. right? It's using more parameters and operators than it needs to be, and has longer circuit depth than needed. You can also take the same operators in your pool and just append them randomly and check what is better, just for some random way of creating the answers, or the strategy of taking the derivative at each step. And what we see here is that the derivative, the gradient criterion, converges much faster. This is a simulation for hydride, but we find similar approaches. Similar results for other molecules. All right, let me now get to the optimization question and how trainable these circuits are. We don't have any issues with trainability in anything we've done. And in fact, we see the opposite, that this algorithm behaves actually quite well. So what we're plotting here is, in the x-axis we have the adaptive iteration. So you should think of, as you move in the x direction, you're adding operators, you're drawing your own sets in your circuit. And in the y-axis again, you have the error from the exact solution. And it's the same answers every time, it's the same form of the operators, and this is what the adapt algorithm gives you. What's different between the different colors is where you initialize it. So if I initialize the parameters randomly, and then I optimize, I get trapped in all these local minima that this landscape seems to have. If I follow the approach of optimizing my parameters by starting with the warm start, meaning the optimized value from the previous run, we're largely immune to all these local minima, and that's what we call here recycled initialization. So it doesn't always hit the global minimums, but it always sort of finds a good minimum. And the way we think about this intuitively is that the algorithm is sort of digging into a minimum it finds. And we're not yet in this over-parameterized regime where pretty much all the minima are good. Okay, so the answer is still short and compact. So I still haven't addressed exactly how we should pick the operator pool. Again, how you choose this operator pool will be critical to how well the algorithm will perform. And one thing you can do is you can take inspiration from the hardware efficient ansatz and build in constraints of your quantum processor. So let's look at some examples of that. So we can take a pool that has weight 4 Pauli strings, and we took inspiration from these double operators, and we just dropped the z strings to get x's and y's only, and we only kept the operators that will give you something non-zero. So what I'll show you next, we're comparing this pool of weight 4 to the fermionic pool, which touches order n qubits. And if I compare the two, again for some sort of prototypical molecules, you will see that for the fermionic adapt, what I showed you before, the red thing, the red, we're converging faster in terms of how many optimization parameters we have. And that's not surprising because this operator pool has a high weight, your Pauli strings have high weight, it does you more qubits, so it's kind of intuitive you would finish quicker. But you're paying the price of a large number of C0s, which of course is not very something you want to do with NISQ processors. So if you use this other pool, what we call qubit adapt in blue, you see that the number of C0s is much, much smaller. Now, that's another pool we tried. Okay, it performed pretty well. There's a lot of work that has gone into how you choose this pool that we have done, and other groups have done as well. And one question is, how can I guarantee that I'm going to choose a pool that will take me to an arbitrary state? Right, so the state you're looking for is an eigenstate of some Hamiltonian. It can live anywhere in some Hilbert space of n qubits. And what you want is to guarantee that the operators that you can choose from can in principle take you to any state. And we've done quite a bit of work on that. We have the notion of complete pools, which do exactly what I mentioned. And basically, you have complete pools when you take a full algebra and you apply it to a random state, you can get to any other state. And one question you can ask is, how big are these pools? Because if you remember, I need to do a measurement for every operator in the pool. So I don't want to do more measurements than I need to do in running my algorithm. And what we have shown is that you need, for the pool to be complete, it has to have at least 2n minus 2 operators. And this is actually a nice result because you see that it scales linearly with the number of qubits, which is something that is about as good as you can hope for. And we've also shown examples of minimal complete pools that are nearest neighbor. So this is pretty good news. The other thing is that we have a criterion that scales polynomially, classical testing of whether a pool, if you give me a pool, I can test if it's complete or not. And another thing you should worry about is whether your pool has the right symmetry. So your problem, your Hamiltonian some symmetries, your eigenstate you're looking for has also presumably some symmetries. You can systematically build in symmetries into your operator pool so that you can actually guarantee that you're not gonna restricting yourself outside the space where your state lives, which is I think what happened in Shulka's example. And there's a lot of work that went into this paper. It's a great work by Vlad. I'm not gonna talk more about it, but I recommend if you're interested in this topic of symmetries and how you choose your operator pool. I recommend this paper. All right, now I showed you some evidence that adaptive algorithms can be superior to fixed ansatz. But we're still, you can still ask, is what I showed you the best way to go about it? So in the example I showed you, I had weight 4 Paulis. So my circuit, in a cartoon kind of way, would look something like that, right? I'm touching 4 qubits every time I run my iteration, I'm touching 4 qubits. And this is a pretty sparse circuit, right? I have a lot of qubits are not doing anything while I'm putting in gates, so I'm kind of wasting a little bit of time where I could be driving more qubits. So what we can do is we can do something more like this, where we're tiling our circuits more tightly. And we call this Tetris adaptive PQE. I don't know if there's people who are old enough to remember Tetris. Maybe it's cool again now. But basically the idea is that you're trying to pack gates as much as you can and shorten your circuit. And how do you do this? You can do this in different ways. The way we went about it is looking against the gradients and not choosing the operators that have not just the largest gradient that adapt criterion uses, but also the next ones, so long as they touch different qubits, so that we could sort of dial the circuit this way. Let me show you some examples of this. Again, these are classical simulations of hydrogen chains, and we're comparing the Tetris adapt approach to the regular adapt versus one operator at a time, and you see that they converge. That Tetris has a shorter circuit depth, shown in blue over here, and the CNOT gates we use here are comparable to what adapt. Okay, so you're actually saving a lot of coherence time, and you're not using more CNOT gates. And then you can also ask about trainability, and you get similar things. We haven't had any issues with trainability in the examples we looked at, and Tetris adapt also seems to avoid all these local minima that you naively have if you didn't know how to optimize, where to start your optimization. So the last thing I want to talk about is going back to this measuring the pool operators. So I already mentioned that within the adapt algorithm, at every iteration, you do a PQE. So in addition to the cost of PQE, you have the cost of measuring these gradients. right? This is the price you pay in order to have shorter circuits. So you could worry about how much overhead does this add to your algorithm. So let's look again at this criterion, right? This is the grading criterion I mentioned. Your Hamiltonian heads order n to the 4 terms. Your Pauli pool also goes as order n to the 4. So if you take naively approaches where you group terms Hamiltonian, you can have a really bad scaling. Sorry, not group terms that occur from this commutator. So the question is, can you do better than that? How would you measure your gradients in a smarter way? So the first observation is that if I have two Pauli strings that commute with each other, then the commutator with another Pauli string, the commutators with another Pauli string A in this case also commute. And this is exactly what we want, right? If I have two pool operators that commute with each other, then I can take a term in the Hamiltonian, which is a Pauli string, and look at, and I know that the commutator of each of these commutes with each other. And for extension, I can then group terms. I can group operator pool terms that commute, and then I know guaranteed that their commutator with their Hamiltonian commutes. So let me just show you this slide. We take an example term Hamiltonian that has all these Z strings, and then what we do is we fix where the Y operator sits. It sits on the first cube over here, and then we vary where the X operators are. All these by construction commute with each other, these S1 through S3 in this case. So I'm guaranteed they're going to commute, the commutators will commute this term. And then I can just count. So I have order n cube of these, and I can, I have n of them because at every point I'm fixing one of the qubits while anchoring this Y operator. So that means that I have an order n overhead only, as opposed to this kind of horrible scaling that you might expect. So this is really good news, and it's encouraging that this could be something that we want to try at some point on the hardware. So before we wrap up, let me also mention that you can use this approach for other things on molecules. All the examples I showed you were for molecules, but you can look at them as matter problems that have translational symmetry. The idea here is that I can help a lot in finding a good pool for the extended problem by solving a small instance of the problem, seeing what the algorithm selects as my pool operators that I use in my ansatz, and then putting those in a pool for the larger system. And we've seen that the strategy works well. I'm not going to spoil it because there's a poster by Garunia that I encourage you to go here and talk to her this work. And then let me also show you other things you can do with this approach. We've done work with QAOA in a virtual call adapt QAOA, where we show that you can get much faster in a more economical way to the solution of QAOA using the adapt algorithm. You can solve other problems like nuclear physics, high energy problems. We have some work on gift state preparation, including thermal field double that you heard a little bit about this morning. There's also cool things you can do to add randomness to the algorithm. And other groups have done a lot of nice follow-up work. I've just highlighted here that you can do time dynamics and not just static problems. So I think I don't have time. The last thing I was going to tell you about was that you can also optimize directly at the pulse level and do the VQE in a much faster way that way. I'm going to skip over to my acknowledgements. These are people from my group who did the work I presented. A lot of the work that Tetris adapt and measuring the gradients are by Peter. All this work is done in collaboration with Ed, who's here, and Nick Mayhall. And then other people who have left the group, and also Christian and Alicia are here at the conference as well. And then, this is really my last slide. I just want to show you our campus. We also have very nice nature. And we have a quantum center with a lot of people. 5 new faculty are joining us this fall. which is very exciting. So if any of you want to visit us and interact with us, all these people in different departments, drop me a line. And there's also postdoc positions in the center. So thank you.
Okay, do we have any questions? Yeah, I was wondering, so you were mentioning thermal states, but could you also prepare some sort of microcanonical state, like a range of energies, not energy eigenstates?
You should. You would need to pick the objective function in an appropriate way. So long as you pick the appropriate objective function the right way, then you can definitely run the algorithm.
Okay, if there are no further questions, I thank Sophia again.